When it comes to modern air defense, the S-400 Triumph is often portrayed as Russia's crown jewel, a system that isn't just powerful, but uniquely suited to challenge America's stealth advantage. The claim is bold that even the F-35 and other low-observable aircraft may not be as invisible as they believe. But how much of that is real? Where does the S-400 truly excel, and where do its limitations lie? Today, we're diving deep into both sides of that debate. At the heart of Russia's counter-stealth argument lies its radar network. Not just one radar, but a layered, multi-band architecture, combining long wavelength systems with fire control radars. The NEBO-M setup is central here. It includes a VHF band, AESA radar, the NEBO-SVU, and L-band arrays such as NIC-G, optimized to pick up unusually shaped radar returns that stealth aircraft are not designed to fully suppress. These lower-frequency radars operate on wavelengths that, unlike the X-band or S-band radars used in many Western systems, interact differently with stealth geometry. In theory, that means they can detect stealth aircraft more reliably, or at least sooner. That detection, however, is only one piece of the S-400's layered air defense. These early warning radars feed information into more precise systems, such as the 91N6 Big Bird panoramic radar, which provides 3D tracking at long range, and the Gravestone 92N6 fire control radar, which guides the system's missiles. By combining data from these different radars, the S-400 can build a more complete picture of the airspace, including anomalies that may correspond to stealth aircraft. This multi-sensor fusion is where much of Russia's counter-stealth philosophy lies. It doesn't rely on a single stealth radar, it relies on a network. Proponents of the S-400 argue that this architecture lets them detect and even track stealth fighters at ranges far beyond what earlier systems could. According to some assessments, the NEBO-M's deployable low-frequency arrays might detect aircraft like the F-35 at very long range, although actual targeting is much harder. The S-400 also includes a family of missiles with layered ranges, shorter-range interceptors for closer, agile targets, and very long-range missiles, like the 40N6, that theoretically enable engagement well beyond what many Western SAMs can reach. On paper, that looks dangerous for stealth. Russia's own sales pitches emphasize the system's counter-stealth credibility. Moreover, some U.S. military officials have expressed concern. Even if the S-400 cannot reliably lock on a stealth plane all the time, its ability to detect and track creates a significant data collection advantage. Yet critics are quick to point out the critical distinction: detection not equals weapons quality targeting. Several analysts argue that these long wavelength radars can pick up the presence of stealth aircraft, but they don't necessarily produce enough resolution or fidelity to guide a missile accurately. For example, a former U.S. Navy operations specialist argues that while the S-400's radar network, especially NEBO-M, might detect an F-35, it lacks the precision in some cases to point a missile reliably. That's not just speculation. The physics of radar working at very high frequency or L-band imposes trade-offs. Lower frequency radars have longer wavelengths, which can help see stealth shapes. But they also suffer more from clutter, like terrain and weather, and their angular resolution is lower. Simply put, detecting something roughly isn't the same as getting a solid, weapons-grade track. The S-400 system may know something is there, but guiding a missile to hit it with high probability is another matter. Historically, integrated air defense systems, IADS, have struggled with this balance. As one defense analyst put it, yes, Russia has invested in low-band early warning radars, but can it use these to put together a track good enough to engage very low observable aircraft? That's a crucial point. Without reliable targeting, detection becomes an intelligence advantage, not necessarily a kill guarantee. There are real-world factors that further complicate the S-400's stealth-defeating narrative. For one, the performance of radar systems in operational environments depends heavily on terrain, electronic warfare, and coordination. High-frequency fire control radars, which are needed to guide missiles, may not always be cued effectively, especially in cluttered or electronic contested environments. Even advanced radars are less effective if their operators lack tactics or integration with other systems. On the American side, stealth aircraft are not sitting ducks either. Advanced platforms like the F-35 rely on more than just geometry or materials. Their electronic warfare suites, like the ASQ-239, can passively detect and geolocate threat radars, helping the pilot or mission system decide when to evade, jam, or strike. Stealth pilots also use tactics, penetrating via terrain masking, coordinating with electronic attack platforms, and using decoys to confuse or saturate SAM defenses. There's also the question of doctrine. Stealth is often not used to fly unchallenged deep into enemy airspace today, but rather to survive long enough to launch standoff munitions, perform electronic suppression, or conduct intelligence missions. The goal isn't always to win a dogfight, but to deliver a capability without being destroyed first. That means that even partial detection, where the S-400 sees something but cannot lock on precisely, might spur changes in how stealth aircraft operate, but may not necessarily neutralize them. In some deployments, the S-400's addition of low-frequency radars like NEBO-M serves more as an early warning or queuing layer than a pure fire control network. Once NEBO-M detects a low-signature target, it can cue higher frequency systems to take over. That's a layered approach, not a silver bullet, and it reflects a more nuanced philosophy. You don't need to be perfect. You just need to be good enough to complicate your adversary's mission. Another factor is interoperability. Integrating multiple radar bands, linking them with fire control, maintaining communications, and processing data in real time is technically challenging. Even if each radar node is capable, the system is only as good as its weakest link. Command and control, operator training, and mobility matter. A static radar is powerful, but a mobile networked radar system that can move, hide, and reconfigure is truly dangerous. And the S-400 is not perfect. Its fire control radars, like the Gravestone, have quoted ranges that depend on target size, radar cross-section, and external queuing. Some analyses suggest that the most dramatic ranges, for example, 250 kilometers for a 4 square meter target, assume ideal conditions in pre-queuing by a panoramic or early warning radar. That means on the ground, in real conflict, those envelope numbers may not always reflect kill-at-will capability against stealth jets. The debate boils down to risk, not absolutes. The S-400 may not guarantee consistent kills of stealth aircraft, but its ability to detect, track, and potentially engage them complicates the operational picture. It's less a matter of stealth is dead, and more stealth is no longer unchallenged. That friction alone forces adjustments in tactics, platforms, and thinking. In the broader strategic sense, exporting the SC-400 to other countries, India, Turkey, China, magnifies its impact. It gives Russia access to data on how stealth aircraft behave against its radars, and it provides potential buyers with air defense grounded in real counter-stealth doctrine. For attackers, that means facing not just a missile, but an entire detection network that's been battle-tested and studied. But for the West, surrendering to that narrative is premature. The F-35, F-22, and similar platforms are still among the most capable aircraft ever built, not just because of stealth, but due to sensor fusion, electronic warfare, and mission flexibility. Stealth is not just about hiding, it's about striking smart, using data, and minimizing risk. And many Western planners believe that smart tactics and networked assets can mitigate or even offset the detection risk posed by systems like the S-400. Ultimately, the S-400's role may not be to dominate stealth aircraft in every engagement. Rather, its strength lies in creating ambiguity, making stealth less of a guaranteed asset and more of a calculated risk. In that sense, Russia's air defense philosophy is not simply about destroying invisibility, it's about disrupting it. So has the S-400 defeated U.S. stealth? Not entirely, but it has certainly challenged it. And in modern warfare, creating doubt, forcing changes, and raising the cost of stealth operations can be just as powerful as destroying an aircraft. The future may be even more complex. Next-generation systems like the S-500 promise even greater reach, faster reaction times, and radar systems optimized to detect new stealth signatures. Meanwhile, Western air forces are evolving too, building better jammers, smarter decoys, and unmanned wingmen designed to overwhelm sensor networks. Russia's continued refinement of its air defense network demonstrates how seriously it takes American stealth as a threat. Since the 1990s, Moscow has invested heavily in digital radar processing, mobile radar arrays, and advanced networking to eliminate the blind spots that plagued older systems. Modern variants of the S-400 and the emerging S-500 now operate within broader defense bubbles that include decoy radars, mobile launchers, and command posts linked via encrypted communications. In wartime scenarios, this would mean that even if one radar unit is jammed or destroyed, others can still maintain coverage. A distributed resilience that forces stealth aircraft to constantly adapt. But while that may sound impressive, it also highlights a central problem. The more complex a system becomes, the more fragile it can be. Networked radar requires vast bandwidth, precise synchronization, and trained operators who can interpret data correctly under pressure. Any disruption, electronic interference, cyber intrusion, or kinetic strikes on relay nodes can degrade its effectiveness. The U.S. military understands this and tailors its strategy accordingly, often emphasizing electronic warfare over brute force air campaigns. In fact, the next-generation electronic attack aircraft, like the EA-18G Growler and future unmanned jammers, are designed specifically to blind systems such as the S-400, long enough for stealth aircraft to enter and exit contested zones. On the ground, the S-400 also faces physical constraints that rarely make it into propaganda. To function at its advertised range, it requires stable terrain, power supply, and properly aligned radar arrays, not always easy to maintain in the field. The sheer size of its radar mass makes them vulnerable to detection by satellites and long-range strike weapons. For that reason, many experts argue that, while the S-400 is formidable in theory, in real conflicts it operates under constant threat of preemptive suppression. The best defense it provides, therefore, may be psychological, deterring attacks by creating uncertainty, even if its practical success rate is lower than claimed. Meanwhile, Western stealth programs continue to evolve beyond simple radar evasion. The U.S. is investing heavily in what's known as spectral management, the ability to manipulate not just radar reflections, but also infrared signatures, electromagnetic emissions, and even acoustic and visual profiles. When combined with advanced networking through systems like Link 16 and upcoming satellite relays, these stealth jets effectively operate as nodes in a larger information web, trading invisibility for coordinated awareness. A single F-35 may not remain hidden from every radar, but when working with drones, decoys, and jammers, it becomes part of an adaptive ecosystem that is far more difficult to counter. Another overlooked element is space-based surveillance. Both the US and Russia are expanding satellite constellations capable of tracking aircraft through changes in atmospheric ionization or contrail patterns. This new domain introduces an entirely different layer to the detection game, one that even stealth technology cannot completely hide from. The more the skies become monitored by space sensors, the more relevant coordination between air, ground, and orbital systems becomes. This evolution hints at a future where stealth and detection no longer belong solely to individual platforms, but to integrated multi-domain networks spanning the entire planet. From a geopolitical standpoint, the S-400's reputation also serves as a powerful diplomatic tool. Its export to countries like Turkey, India, and China isn't just about sales, it's about influence. Owning such a system sends a signal of independence from Western military technology, and its presence can deter potential air incursions, even if no missile is ever fired. However, these same exports risk exposing its capabilities to adversaries. Every time an S-400 battery operates near Western aircraft, data can be collected, analyzed, and used to improve countermeasures. In this way, Russia's pride in the S-400 may paradoxically accelerate its own obsolescence by revealing its electronic fingerprint to the very nations it aims to deter. On the American side, the countermeasure industry is thriving. Specialized firms develop radar-absorbing coatings, frequency-hopping communication systems, and deployable decoys that mimic the radar signature of an F-35 or B-2. These decoys can trick air defense operators into wasting precious missiles or revealing their radar positions. The cat-and-mouse dynamic has become so sophisticated that in some exercises, air defense units have reportedly been overwhelmed by the number of false returns, struggling to differentiate real aircraft from phantom echoes. At the same time, stealth technology itself is evolving toward affordability and scale. Where earlier designs like the B-2 Spirit were prohibitively expensive, newer systems such as the B-21 Raider promise similar low observability at a fraction of the cost. This democratization of stealth could soon enable fleets of drones, bombers, and fighters to operate in swarms, each with partial stealth features that, when combined, saturate radar networks. The S-400 may be able to track some of them, but not all at once. The battlefield of the future will likely be defined by this kind of asymmetry: quality versus quantity, precision versus overwhelm. One more factor that rarely enters public discussion is the human element. Despite the automation of radar and missile systems, skilled operators remain the decisive link between detection and destruction. Training, fatigue, and decision-making under pressure can make the difference between a successful intercept and a missed opportunity. Stealth pilots, too, rely on experience to exploit the smallest radar gaps, flying routes that thread through complex detection geometries. This human-machine interaction ensures that the stealth war will never be purely technological. It's as much a test of minds as it is of machines. Finally, there's the question of perception. Stealth aircraft and systems like the S-400 are not just military tools. They are symbols, embodiments of national pride and industrial capability. When a nation claims its air defense can see the unseen, it projects confidence, strength, and deterrence. When another showcases aircraft that can evade the most advanced radars, it sends a message of superiority and innovation. In many ways, this duel has become a psychological theater as much as a strategic one. The reality likely lies somewhere in between, a constant balancing act where advantage shifts with each technological leap, tactical adjustment, or battlefield encounter. In the end, the competition between stealth and detection is a technological arms race, not just in hardware, but in algorithms, tactics, and strategy. The S-400 is a major chapter in that story, but it's far from the final word. If you found this breakdown helpful, drop a like, subscribe for more deep dives into air power debates, and ring the bell so you don't miss our next video, where we'll explore how hypersonic weapons are changing interception theory forever.